In previous episodes, we analyzed world models that were built by design, from Kalman filters tracking missiles using linear algebra to Dreamer v3 mastering 150 different environments. These systems possess an explicit module dedicated to dreaming, planning, and simulating. But what if you don't need to build the module on purpose? Consider GPT-4. It is merely predicting the next token. Yet, to successfully predict a physics textbook, it must understand gravity. To predict a mystery novel, it must understand motive. The provocative question at the frontier of AI is this: do large models trained on massive prediction tasks implicitly learn physics, logic, and causality as a byproduct? Are they simulating the world just to predict the next word?
To understand how this might happen, we have to go back to 2018 and a paper by Vanden Oord and colleagues, Contrastive Predictive Coding, or CPC. They wanted to learn representations without labels. The obvious way is to predict the future. If you see a video of a dropped ball, predict where it lands. But there is a trap. If you try to predict the raw pixels, you face a combinatorial explosion. Look at a tree swaying in the wind. The exact position of every leaf is high-frequency noise. It is chaotic. Predicting the exact pixel value of a leaf edge is impossible and useless. That is high-frequency noise. CPC introduced a crucial shift. Stop predicting pixels. Start predicting slow features, the objects, identities, and semantics that persist over time.
Here is how CPC ignores the noise. It starts with a nonlinear encoder. For audio, this is a 5-layer strided convolutional network. It takes raw 16 kHz waveforms and compresses them down to a latent vector, Z. This Z represents just 10 milliseconds of sound, but it strips away the phase noise, keeping the phonemes. Next, an autoregressive model, typically a GRU, ingests all previous Z vectors and summarizes them into a context vector, C. Now, the critical move. Instead of decoding C back into pixels or audio to predict the future, CPC stays in the latent space. It uses a linear transformation to predict the future Z vectors directly from the current C. But how do you train this? You can't use mean squared error on latent vectors that are constantly changing. You need contrastive learning. The mechanism is the InfoNCE loss. The model is given a context, C, and a bag of possible futures. One future is the real one, the positive. The others are random snippets from other parts of the dataset, the negatives. The model calculates a compatibility score, essentially a dot product, between the context and every candidate, normalizing them exactly like a softmax classifier. By forcing the model to pick the one true future out of n negatives, you are maximizing the mutual information between the context and the future. The model learns to encode exactly the information shared between past and future, the structure, and discard the noise that is unique to the moment. The power of this approach is its universality. The exact same logic worked across 4 radically different domains. In audio, using the Libri speech dataset, linear classifiers on top of CPC features achieved 97.4% speaker classification accuracy. It learned to recognize voices without ever being told what a speaker is. In vision, on ImageNet, it outperformed previous unsupervised methods by 9 absolute percentage points. In reinforcement learning, simply adding this auxiliary prediction task to an A2C agent improved performance on 4 out of 5 DeepMind Lab navigation tasks. Predicting the future helped the agent understand the maze. Fast forward to 2023. Researchers Lee and colleagues took this idea to the extreme. They trained a standard GPT model on Othello. The training data was just text, C4, E3, D3. No board images, no rulebook. The model became great at playing Othello. But here is the shock. When they used linear probes, simple detectors, on the model's internal layers, they found the board. The model had spontaneously reconstructed the 2D geometry of the 8x8 grid inside its high-dimensional vector space. It knew which tiles were black and which were white, and they proved it was causal.
They manually flipped a bit in the model's internal representation from black to white. The model immediately changed its next move to respond to the new, hacked state. It wasn't just memorizing statistics, it was maintaining a dynamic world model.
This leads to the great debate regarding large language models. Do they have world models, or are they, as Emily Bender calls them, stochastic parrots? Jacob Andreas argues that LLMs act like Kalman filters. They maintain a belief state about the world that updates with every token. The Othello result supports this. However, skeptics argue that text is a lossy projection of the world. You can learn that dropping correlates with falling, but without sensory experience, the model lacks grounding. The synthesis view is that LLMs likely have approximate world models, good enough for common situations, but brittle when pushed out of distribution.
But what if we move beyond just text? DeepMind's Gato model took the predict everything philosophy literally. It was a single transformer trained on 604 different tasks: Atari games, robot arm control, image captioning, and chat. The innovation was tokenization. Robot joint angles became tokens, image patches became tokens, text became tokens. Gato predicts them all using the exact same weights. The fact that one set of weights can model the dynamics of a robot arm and the grammar of English suggests that prediction is a universal solvent. If you can predict the token sequence, you have implicitly modeled the underlying system generating it.
However, LeCun argues we are still doing it wrong. He points out that language is extremely low bandwidth. Human speech is about 40 bits per second. Vision is 10 megabytes per second. A model trained only on text is starving for information. But remember the CPC lesson. Don't predict pixels. LeCun proposes JEPA, the Joint Embedding Predictive Architecture. Like CPC, it predicts in latent space, but unlike CPC, it abandons contrastive learning. Contrastive learning requires negative samples, which get inefficient in high dimensions. JEPA simply predicts the representation of view Y from view X, using architectural tricks to prevent the model from cheating by predicting a constant zero. It is the logical evolution of the world model hypothesis. Learn from high-bandwidth sensory data, but predict only the abstract structure.
So, do large models have world models? The evidence from CPC, Othello, and Gato suggests the answer is yes, but with caveats. They don't have world models because we programmed them to. They have them because the most efficient way to compress and predict a complex data stream is to understand the rules that generated it. In the limit, perfect prediction requires understanding. We are no longer building world models, we are growing them.